Hello everyone and welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. My name is Paul Tingler. I'm the Director of Web Seminars at NSTA and I'll be moderating tonight's program. Our presentation this evening is the first in a series of programs with the American Chemical Society Middle School Division, and it's entitled Matter, Solids, Liquids, and Gases, introducing a free online resource for middle school chemistry. Our presenter is Jim Kessler. Welcome, Jim.
Thanks, Paul. Hi, everybody. It's good to be here. Thanks for coming. We are ready to start. Today's presentation is about middleschoolchemistry.com. It's a free online resource of lessons of basic chemistry concepts. Tonight, we're going to talk about Chapter 1, Solids, Liquids, and Gases. We're going to take a quick tour on the web of middle school chemistry just to talk for a minute about what it is. Basically, it's 6 chapters of activity-based lesson plans that teach very basic ideas of chemistry at the middle school level. Things like solids, liquids, and gases, what we'll be doing tonight, state changes, density, different ideas of solubility, a little bit about the periodic table and bonding, chemical change versus physical change. So all of those ideas that you would work with students at the middle school level. But one of the key features of middle school chemistry is to help students design valid experiments. We present them with some kind of observation, either through an activity or a demonstration, and ask questions and try to get kids to investigate, to design experiments, to find things out about what they've observed. We can take a quick look. I'll take you to the web, to the site. Let's see. Now, for this web tour, the way we're going to do it, I will take you to Chapter 1 and to a lesson, let's say the first lesson in Chapter 1. And just to give you an idea, I think that you guys have to scroll down yourselves. So if you scroll down a little bit, you'll see that this is a lesson. This is lesson 1 in Chapter 1, and it starts with, it has some key concepts that are covered in the lesson, a summary, the objective. An evaluation is a student activity sheet. It's a formative kind of assessment so kids can record their observations and answer questions. If you scroll down a little bit more, I can't lead you through this. You have to do it yourselves. You'll see there's materials for a demonstration, and then there's a little bit of information about the lesson, and then we start. All the lessons are in a 5E format. We start with some kind of engage, either a simple activity or a demonstration to get everybody on the same page, and then the idea is some question will arise out of that engage. And so after that, if you scroll down a little bit more, you'll see that we do an activity to explore something. So you have engage and then explore. Then there's, if you come down more, eventually you'll see that we show kids what's going on the molecular level, either through an animation or modeling that kids will draw. So there's a lot to this. Also, if you scroll back up again and look on the right, there are PDFs of the lesson itself, the activity sheet answers, entire Chapter 1, and there's ways to go directly to multimedia. So there's a lot here. I'll get out of here and come back to the presentation now. So basically, these 5E lessons are designed to be used either, we don't pretend that this is a full curriculum. We really think that teachers will mostly use it to supplement what they're already using, either by using the animations or modifying the activities in some way. So there's a lot there that you can use. This slide just sort of summarizes the main components of a chapter. It's got lessons, and inside the lessons, there's, let's see, there's hands-on activities, student activity sheets, there's multimedia, there's extra teacher background in the form of either written teacher background information, or there's also screencasts. There's like videos explaining some teacher background. There's student reading at the chapter level, and there's also a test bank of questions if you want to make your own tests for kids. So in this webinar tonight, what we're going to try to do is just show you some activities from Chapter 1 and how they could be used with students. Normally when we present in person, you would be doing the activities. We'll show you videos of some of them and describe some of them. But a lot of it will be reviewing some chemistry concepts that are covered in the Chapter 1 lessons that you can do with students. So there'll be a kind of a heavy emphasis on the animations and explanation. But first, Paul, I'll leave this up to you in a second. Here's a way we can sort of gauge your interest in this question. The big idea for Chapter 1 is, why are different substances solid, liquid, or gas at room temperature? This chapter does not talk about the change in state from, let's say, a solid to a liquid or a liquid to a gas. It's really about, why is something a liquid at room temperature? Why is something a solid, for instance? And a sort of a sub-question is, what happens when you heat them and cool them, but not to the point of changing their state? So Paul, could you take over from here?
Sure, thank you, Jim. And I'm going to give you back the tools and ask you to once again use the clip art in row 7, and go ahead and place a piece of clip art along the continuum here to let us know where you are, from having never thought about it and happy that way, all the way up to stay up at night pondering this question, and anything in between there. So again, use your clip art in row number 7 of the tools, and I think that most people are on their way with that. We'll give you another moment to respond, but in the meantime, I'll pass the mic back to you, Jim.
Okay, thanks, Paul. Oh, good. It looks like the majority of people are at least willing to listen if it doesn't take too long. And there are a few people who stay up nights, like I do, pondering this question. So the level of interest is there, so let's keep rolling. Okay, I want to ask you guys to participate again. And this is the way we start Chapter 1, Lesson 1, is we ask kids, you know, this idea of matter, what is it? Anybody have any ideas? What's an example of matter, for instance?
Thank you, Jim. And what we're going to ask for you to do here is to, once again, use the tools, and in this case, grab a text box and drop some ideas there in your text box with either a word or phrase. And if your text box overlaps somebody else's, don't worry, we can move them around once you're done. Just once you're done typing, just kind of leave it there, and I can move them about if you keep it brief to either a word or a short phrase, so that we can leave room for a number of different phrases and responses from people and still have room to spread them around. So go ahead, make your responses, and while they're doing that, I'll try to move them to make them more readable and give the mic back to you, Jim.
Okay, yes, people are writing some good answers here. There's some that look like you've read a textbook. Anything that has mass and takes up space, very good. Plastic and water and stone and diamonds and rocks and air and even plasma. Yeah, the idea here in the classroom would be just to have kids say, I don't know, stuff, my desk, the floor, the air maybe. We just want a nice sort of example of different things, solids, liquids, gases. We want eventually to talk about water. So we kind of, in lesson 1, we ask kids, okay, all this stuff is matter. If they haven't come up with water, we say, how about water? Is a liquid matter? Could that be? The idea eventually is that all this stuff, everything you can touch and see is matter, and that we want to investigate water in particular to start this lesson or this chapter about solids, liquids, and gases. So the way we do it is a very, very simple activity where kids put water on on wax paper. We put some wax paper on a piece of cardstock, and here's Paul. You can run this video, and we'll take a look at it real quick. So basically what we ask kids to do is just put like 5 or 10 drops of water in the same spot on wax paper, and just give us some observations. What's it look like? Does it spread out? Does it stay together? How about if you move the card around, what does it do? And, you know, kids say, oh, wow, it stays together. How about if you try to get it apart? And you can use a popsicle stick to try to split it into 2, you know, relatively equal-sized pieces. It's not so easy to do. Sometimes you get a little bit of water off, like I did that time. The idea is to try to split it into kind of 2 relatively even drops, kind of like that. It's not so easy. And then we ask kids, how about putting it together? Is that also difficult, or is that easy? Let's just put the drops together, and they go together very easily. So the point of this activity, although it's very, very simple, let's see. Oh, yes. Although it's very, very simple, it's kind of powerful because it's very obvious that if water is made of particles, we tell kids, let's assume or imagine the water is made of these tiny, tiny, tiny little particles. Would you say they're attracted to each other or not attracted to each other? And based on that simple experiment, the kids naturally say, yeah, they seem like they're attracted to each other. They were hard to get apart, and they came together easily. So then we go on to another idea, and that is, what else about water? Let's assume, okay, it's made up of these tiny little particles that are attracted to each other. What else could we learn? So, Paul, you can run this if you want. This is a demonstration, or you could either do it as a demonstration or as an activity, where you just put 1 drop of food coloring in water, and the question is, why does it do what it does? It doesn't just sit at the top. It doesn't go down to the bottom and just sit there. Something's happening here. And we ask kids, you know, if water molecules are attracted to each other, well, why would this happen? Let's say food coloring is made of tiny particles too. Why might it be that it spreads all throughout the water? What could that be? So maybe kids might suggest, Paul, do I? Oh, I see. Maybe kids will suggest that the particles move. Maybe the water molecules move. Maybe the food coloring molecules move. Maybe they all move. So we take those ideas and we look at a model. Here's our model of water, and you can run this animation, and we'll take a look at it. The idea is, it's called particles of a liquid, and if you go down there to the lower left where the arrow is and you go over, it'll say play. Just click that so it plays. And then you should get a cup that looks like it has a big, well, anyway, it's supposed to be water, and you have a little zoom in feature with a magnifying glass with a plus sign. If you hit that, you should get little spheres that are moving all around. So this is our model for kids, that water or any liquid is made up of little particles that are, you can see they're kind of attracted to each other, that they don't zoom all apart really, really fast. They're kind of all clustered together, yet they're moving past each other. If you can kind of keep your eye on any one of them, it doesn't just vibrate in a fixed position. It moves with respect to the other ones, and it actually changes its position. So this is our model. Now, I'm going to zoom out by hitting the magnifying glass with the little minus sign on it, and then stop, and then we can go back to the presentation. So the idea here is, like, let's help kids understand water or any liquid on the molecular level by using models. So this was an animation, which is a model, but there's other models too. I mean, on the activity sheet, this is a little section of the activity sheet here. Let me grab a hand. If you look, this is a simple drawing that a kid can make. He or she can draw circles that are kind of near each other. Not, you know, there's enough, a little bit of space between them that you could imagine them moving past each other, but there's no way to make them move, so you have to draw these little motion lines. So we have 2 motion lines for water at room temperature. We use 1 motion line for cold water, 3 for hot, and 2 for room temperature. So what we would do is have kids draw this and then make a caption underneath that describes what their drawing means. So they've seen the real thing, they've seen water, they've seen some evidence that it's attracted to itself and that it's in motion. They've seen an animation which suggests those ideas about water, and now they are drawing. So as many different ways as they can, we're trying to help kids imagine a liquid at the molecular level. It's hard to imagine something that you can't see. Now, on this one, you can run this. This is a video that we picked up off of another site, which we think is legal. And it's a guy, he bursts a water balloon, and then if you show it in super, super slow motion, you get this cool effect of the water staying together. And in fact, kids can actually do this. I used to do this when I was in a pool. If you take some water and throw it up in the air in the right way, kind of gently, you can see the globule kind of stay together. And now there'll be a close-up of that same thing happening. So it kind of keeps the shape of the balloon, and you can see how, you know, water must be attracted to itself. It's cheating a little bit because it's in such super slow motion, but it's still, you get the idea of attractions. So we can go back. Now, there's also, there's an extend portion at the end of each lesson. The 5 E's would have an E at the end, which is extend for us. And in this particular case, we have a game where you can take make a raceway, which is just a curvy path, and put that put wax paper over it, and then put drops of water here together to make a drop, and then you kind of tilt your race drop raceway to have the water drop move along the path, and you try to beat the person doing it next to you, and you, I don't know, get a time penalty. If you hit the edge, you got to try to keep it in the middle. If you've got littler kids, you could make the path wider. If you've got older kids, maybe you could make it narrower. But it's the idea that you can have fun with this interesting characteristic of water, that it's cohesive, that the particles are attracted to each other. There's another little game too, water drops unite, where you take the water drops and put them on the outside of a circle, and you see how long it takes you to move them all to the center and have them unite as one drop. So it's just sort of a follow-up. Okay, now later chapters of middle school chemistry deal with this sort of the more molecular view of water. I'm showing this to you guys now just as sort of kind of background. Many of you may already be very familiar with this idea, but the point is, we've talked a couple times about water molecules being attracted to each other. Well, why is that, is the question. You can run this, Paul. It's a video that we have on the site. It actually, like I said, comes up later in chapter 2, but water is made of 2 hydrogens and an oxygen. This is a ball and stick view. This is called a space filling model. Let's go to the next slide, or back to the presentation, and we'll just see that you guys just saw this. Let oh, let me grab a hand here. This view of the water molecule, the space-filling model, has the two hydrogens here, and the oxygen, the big red one here. And the idea is that they're covalently bonded. Now, we're not going to spend much time on this, but covalent bond is a sharing of electrons, as you probably know. And in a water molecule, they're not shared perfectly equally. They're a little more attracted to the oxygen than they are to the hydrogens. So since electrons are negative, and they're attracted a little bit more to this oxygen, this area of the model of the water molecule ends up to be a little bit negative. And since the electrons from the hydrogen spend more time up here and less time here, and they're negative, since they're spending less time here, the hydrogen area is slightly positive. Anyway, you probably, many of you probably know this, but the water molecule, therefore, is a polar molecule. It's neutral throughout, but its charges are kind of separated. This model here is called a charge density model. It just shows that this sort of very light gray area is a bit more positive, and this darker area is a bit more negative. It shows where the electrons are. So the consequence of all this, here, let me, well, I guess I'll keep that, is that water molecules tend to attract each other. So you have the positive area of one molecule sort of associating with or attracted to the negative area of another. So really this is more for you, or maybe if your kids are ready, you could begin this kind of explanation. But this really comes a little bit more later in the lessons, in later chapters. Let's go on here. We'll pause for questions, and I'll let Paul take over here for a minute.
Thank you very much, Jim. And if you do have questions on the information that he has presented to this far or the resource itself, please do go ahead and drop those into the chat at this time. Also would encourage you to drop particular resource questions into the chat throughout, as again, Jim is joined by his colleagues, Adam and Patty, and they can also respond in the chat to your questions. So if you have questions about anything that we've seen so far, go ahead and drop that in this time. I do see several people typing, so I'll wait until I get a question, and then I'll pass it over. And I see the first question there from Christy. Are the resources downloadable or just to be viewed online? Jim?
Yeah, everything you saw here is downloadable. We are really encouraging teachers to use these in any way they think will be valuable for classroom use or for professional development. Yeah, we encourage you to download them and use them.
Great, thank you. And I see a question from Nancy there. She says, what do the accompanying student readings look like?
Well, the student readings, what we try to do is go back and look at the main points from each lesson in the chapter. So for the student reading for Chapter 1, basically what we did was to cover the ideas that you'll see today in, like, what is matter, what are the characteristics of a liquid, a solid, a gas. It's really sort of like maybe a textbook sort of approach, but referencing the activities and the content from the lessons, but not relying totally on them. I hope that was okay.
Great. I see a question there from Bianca. She says, would you recommend students actually visiting the website and becoming independent, self-directed learners?
That we did not create the site for that purpose. We really believe it's a teacher-mediated, resource, that there's lots of really good questioning that the teacher would use to elicit, like, sort of valuable inquiry kind of ideas from kids. It could maybe be used that way, but that's not the way we designed it, and I think it'd be a lot more valuable with a teacher taking kids through this in the way that it's intended.
Great. I think we'll grab one more. I see Patty and Adam have also grabbed some, so I appreciate you guys doing that. But I saw somebody that asked a question about the polarity of the water molecule. And if you could just go back to that slide and walk through that one more time.
Paul, do you mean actually go back to the slide and run the animation?
No, I think just the one with just the slide itself that showed the polarity of the water molecule, and there you go. I think that's the one.
Yeah, what we're trying to show here, if someone asked, why don't they just stick together like a solid? That's a great question. I think I may have seen that in the chat, but the reason they don't stick together is because these are part of their characteristic property is that at room temperature and at a range of temperatures, they have enough energy and enough motion to overcome these attractions so that they're not held together as a solid. It's actually a very good question. It's the point of the whole chapter, really, is that the reason why any substance is the state that it is, in this case, the reason why water is a liquid, is that it's a balance between the attractions between its molecules and the motion at a given temperature. They're close enough together that they're a liquid. They're not a gas. Their attractions bring them close enough together to hold them together, but their attractions are not so strong that at this temperature they're a solid, so they don't stick together. It's a balance or a competition or a give and take between the attractions and the motion at that temperature.
Great. Thank you, sir. Let's go ahead and move on.
There we are. So what we do next is, this picture kind of gives it away, but what we do is ask kids, how could we test whether heating or cooling a liquid has any effect on the speed of molecules? Actually, what we ask them is, I think the question is, how could you affect the speed of the motion of the water molecules? If you remember, all we did before was we put a drop of food coloring in room temperature water, and we saw that that the food coloring moved, and we sort of concluded that maybe that's because the water molecules themselves are moving. And then we tried to model that. Yeah, that's not a bad idea. So now the question to kids is, how could we test, or is there a way to affect this motion? How could you make it go faster or slower? So lots of kids will say, well, you could boil the water, because they know that makes water move because they see it. They see it move. So one of the big ideas in middle school chemistry is to come up with a valid experiment. So if a kid says, well, you should heat some water and see what happens, or if another kid says you could heat some water and cool some water, well, we ask the question, how would you actually do that? Would you use the same amount of water? Would you use the same type of container? Is it okay to use a few drops of water in one and a whole cup of water in another? Would that be okay? Would it be okay to use a metal cup and a wooden cup? I mean, that's kind of a weird idea. But how would you do this so that it's a fair test? So here's what we came up with. And based on the first activity the kids did with the one food coloring drop in room temperature water, we would hope that maybe they could use that experience to come up with this idea, okay, let's take cold water in one cup and hot water in the other. Let's use the same amount of water. Let's put the food coloring in at the same time and see what happens. So let's run this, Paul. Again, it's a very simple experiment, but we use a blue and yellow food coloring at the same time, just to get a better sense of the mixing, when it turns green. So, sorry, it went pretty quickly, but the hot one is on the right, obviously, and the cold one is on the left. If you guys do this, or many of you probably have done it, we use a very big temperature difference between them. We use very cold water. It had ice in it before we did this video. We took the ice out, so it was nice and cold, and we used pretty hot water on the right. And so the whole point is that heating increases molecular motion. Cooling decreases molecular motion. And it's a pretty obvious difference between them. So then the idea, okay, we have a model now of these particles that are attracted to each other and in motion. If you heat them up, they move faster. If you cool them, they move slower. Let's see if we can have another version of that model. We just have it in our head now from the actual experiment. Okay, Paul, let's take a look at an animation. On this animation, the idea behind it is to go down and hit play, obviously, and then to click on that slider and move it to the right to heat the water up. You should be able to see that the particles move faster. Then to move it back to the left to see that it moves more slowly. For me, it helps to do it a couple times. So I move it to the right, and it moves faster. I move it to the left, and it's slower. Now, one thing we tried to show, and I'm not sure if you think it's too subtle, but when you move it to the right and heat up the water, we want the particles to move faster, but we want to suggest that there's a little more blue space that you see, that the particles are a little further apart. Not only moving faster, but a little further apart. Now, if you think that's too subtle, you can just do what I would do, which is tell kids, maybe that's not right, but I would do that, see, there's a little more blue space there. They're not only moving faster, but a little further apart. So, Paul, can we go back to the presentation? So the idea of this faster and further apart is a big idea in chapter 1. If particles are attracted to each other and you can make them move faster, that motion is going to compete with their attractions, and they're going to be able to be a little further apart. If you slow them down, their attractions are going to be able to act on them a little bit better because they don't have all that motion competing with them, and bring them a little closer together. So this idea of the effect of heating and cooling is a big part of this chapter. So here, this slide is just a sort of a review or a synopsis of what we've done so far, and we do that also in the lesson. Is have a point where, okay, let's think about what we did here. We know that we saw that particles, or we saw water, seems like it moves, seems like it's attracted to each other. When you heat it, it moves faster. We saw that with the food coloring. When you cool it, it moves slower. And then in the animation, we said that it also moves a little further apart when it moves faster. And if you remove energy or cool it, it moves slower, and the attractions cause the particles to move closer together. So that's that was all lessons 1 and 2. And you could use them any way you want, just the animations or just the video or the activities themselves. But we think it's a good start to get kids thinking about matter on the molecular level without overwhelming them, we hope. And then in lesson 1.3, which is that's the third lesson in chapter 1. Chapter 1 has 5 lessons, and we're just going to go through very basics of each one, and we're on the third lesson right now. Here's a question. We give kids student thermometers, and we ask them, what is that red stuff? And, kids look at it, and they're pretty sure it's a liquid. That's not too hard. That it's, we tell them it's alcohol. It's been colored red. And what happens if you put it in hot water? What happens if you put it in cold water? So that's a very simple experiment. We realize that. But you can get to some big ideas if you let kids do it. So they take their thermometer, and they look closely at it. And we talk a little bit about thin tube and the outer tube and the scale, if you want to do that. And we put it in hot water, and you see that the liquid goes up. And then we put it in cold water and see that the liquid goes down. Now the question is why? What's based on what we already know about the properties of a liquid, why would the alcohol do that? So what's a model that could work here? Paul, could you load this animation? Again, this is a, you guys can go down and play this one. On this particular one, if what we're showing, at least on my view, is room temperature first, that these are particles, these are alcohol molecules, and if you go to hot and click it, they should move faster and theoretically slightly further apart, and the temperature should go up. The liquid in the big thermometer on the left should go up. If you go over to cold, they should slow down and get closer together, and it should go down. And it's basically the reason why we're doing this is to give kids a practical application. They've used thermometers probably many, many times, and I think it's not that often that teachers get a chance to talk about how they actually work. I'm going to stop it, and can we go back to the presentation? They're actually a great little device for talking about this idea that particles are in motion, and if you heat them, they move faster and they get a little further apart. If you cool them, they move more slowly, and their attractions bring them closer together. So it's a quick and easy way to get to that idea. Here, we can pause for some questions. Paul?
Thank you, sir. Once again, and I know Adam and Patty have both been at it with the questions there, but I see one coming up from Karine who said, would it be possible to introduce thermodynamics at this point for advanced learners? Could entropy and enthalpy be introduced at this point? Jim?
Yike. I might have to turn this one over to someone else. We don't touch entropy in middleschoolchemistry.com. I guess, to me, it almost seems more about heat transfer than enthalpy. I don't know. We usually use that term for, like in chemical change, or even, I suppose, in a physical change, when there's a change in temperature, we might talk about, an enthalpy change. For these, we're thinking, at least I'm thinking, that if you put the thermometer in hot water, you get heat transfer from the water to the glass of the thermometer to the liquid, which causes increased molecular motion, and you get the result that we saw. Anyway, we do have in, let me think, in Chapter 2, we do, the first lesson is about heat transfer. We don't use it here, but maybe you could get to that idea. I hope that's an okay answer.
Thank you, sir. And see if I can catch another one there. I know, again, your colleagues have done a great job, and I don't see anybody else shooting at a question at this time, Jim, so let's go ahead and move on.
Okay. So here we are already in lesson 4 of chapter 1, and this is obviously a big old anvil. It's a big hunk of solid metal. I don't know, this probably shows my age. I was thinking everybody would know what an anvil was, but I guess kids probably don't know. I guess I'm thinking about the Roadrunner cartoons or something, but to me that was a big hunk of solid. So what we do, this lesson, lesson 4 on chapter 1, is pretty simple. It's really mostly a demonstration and then a modeling of what students saw. And this lesson actually is a good example of, something that's short, that you could do easily to get to a main point. It may not be a full 45-minute lesson, but given what students already know, you could present this material as how is this, how can we relate what we already know to what we're going to see here? Well, let's see. Paul, you can run this. This is the famous ball and ring demonstration where you take I think it's a brass ball, and you show that it fits very snugly through that ring. It's machined in a way that just barely fits through, but it does. Then you heat it up like in a Bunsen burner. If you try to do it on a candle, it's not hot enough. And then you try to push it through, and it doesn't go through. And what's up with that? Why did that happen? And now we'll cool it off, and you can do a lot of prediction on this one with kids, ask them what they think might happen, and it does go through. So you can go back to the presentation. Based on what we know so far, how is that possible? What might a solid be like that caused that to happen? So again, we need a model. And all this time that I'm presenting this, I'm talking about these animations, but there's also lots of drawing and explaining that kids are doing on the activity sheets so that they have lots of different ways of seeing this and dealing with it. The physical way, the animation way, and their own drawing and explaining. That's really, I think, the way to do this so that most kids will eventually get the idea that about solids, liquids, and gases at the particle level. So on this one, Paul, you can run this animation. Here, you can go down and hit play, and you see that mine started with solid, and that they're in, they don't move with respect to each other. They don't move past each other. What's happening here is that they're doing that classic thing you always read about. They're vibrating in fixed positions. Now, if you click liquid, you can see that, okay, there's a pretty big difference between liquids and solids. Although, you have to say that, still the particles of a liquid are relatively close together. They're attracted to each other, but they're moving past each other. If you kind of toggle back to solid, they're also, they're pretty near each other too, not necessarily closer or further than a liquid, but the big point here is that they're not moving past each other. So the question for kids is, like, would you say that the particles of a solid are more attracted to each other than the particles of a liquid, or less attracted? And the kid, I think, should say they're more attracted to each other. Look, they can't even get past each other. Their attractions are strong enough that at room temperature, that attraction is keeping them where they are. Even though they're in motion, the motion isn't great enough to overcome that attraction. So there's an opportunity to talk about that balance between the attractions that particles have for each other and the motion they have at that temperature. That combination determines what state they're in at that temperature. And that's a key to this whole chapter. So again, we hit this point that we did with water, a liquid. What happens if you heat it and cool it? What happens to the particles? We do that also with a solid. And we have kids draw this idea and see it also in an animation. Let's run this one, Paul. So you guys know how to do this by now. If you go down and click on this one, when you use the slider, the particles move faster and they get a little further apart. On this one, we may have actually overemphasized the distance apart as they get hot, but in any case, the particles still don't go past each other. It's not a liquid. It hasn't melted yet. And the idea is that when it's cooler, they move slower, and their attractions bring them closer together. When it's hot, they move faster, and that speed overcomes their attractions enough to make them a little further apart. And that explains what happened with the ball. We can go back to the presentation. Given that idea and that visual, kids can easily then fill in on their activity sheet the pictures of the brass ball at room temperature, when it was heated. Why didn't it fit through the ring anymore? Well, it must be that the particles got a little further apart. Why did they get further apart? Well, because their motions competed with their attractions enough that they could move a little further from each other. And that made the ball big enough that it couldn't fit through the ring anymore. And then on the opposite side, when you cooled it, it slowed the particles down. Their attractions were able to bring them closer together, and it was able to fit through the ring again. So it's just a way to kind of give a particle level explanation for what they saw that makes sense. Now here, this is not in chapter 1, but I put it here for you guys because we talked about why water molecules are attracted to each other, that idea of polar molecules. Here, why are metal atoms attracted to each other? This whole thing of metallic bonding, we're not, at least our opinion, is that it's not necessary to go into this with students. But I thought, if it's not the same thing as the water molecules, it's kind of different. In a metal, many of you may know this, that the outer electrons, at least some of the outer electrons, are leave the metal atom, and it actually causes a metal ion, if you're going to be technical about it. Here, let me grab a pointer. These all have pluses on them because they lost an electron, one or more electrons, and now the electrons are just moving within this big matrix of billions upon billions of metal atoms, which are now ions. And the attraction kind of is these positive metal ions in a sea of electrons is what they usually say about metallic bonding. Again, not important for kids. If for students, we think that if you just refer to the particles of the metal as metal atoms, you're good, and that they're attracted to each other, and that motion affects their distance apart. Okay, we can keep going. And here's just a sort of a synopsis of what we know about solids now, is that they move at a certain speed at room temperature, but their attractions are so strong that they keep, that motion doesn't allow them to move past each other. They're in fixed positions. So it's, again, a combination of attractions and motion. If you add energy, you increase their motion, and you cause them to move a little further apart. And if you take energy away or cool them, it decreases the motion, and they move a little closer together. Their attractions are able to bring them closer together. Let's pause for questions. I'll send this over to Paul.
Thank you again, Jim, and go ahead and pause to take any of your questions you may have. Again, thank you to Adam and Patty for dialoguing, and not only questions there, but I see also people sharing pedagogy ideas and so forth, and again, we appreciate you doing that. So go ahead now, though, if you have any questions for Jim about any of the information that you've seen there, we'll go ahead and pass them over to him. And once again, if we don't happen to get to your question, I'm sure that somebody will go ahead and pick it up in the chat. So if you do have a question now, go ahead and place it in there. I do see a couple of people typing, so I will hold out until they complete their thought. See, some people are still talking about some of the earlier topics as well, but there are a couple still typing, so we'll give them a chance to see if they have a question. I guess most of it's the dialogue that was going on from the earlier one, and this is a nice thing about having a couple of people on your team in the chat. It looks like they're able to address most of the questions there, so I guess we can go ahead and move on, Jim.
Okay. So at this point, we've looked at the first 4 lessons from Chapter 1. This is the very beginning of Lesson 5, the last lesson in Chapter 1. And the idea is, okay, we understand something about the particles that make up liquids and something about the particles that make up solid. What about gases? By this time, we've established, at least as best you can with middle schoolers, that a gas is matter. There's something there. But this activity helps kind of drive that home. We want to find out what's a gas like and what happens to the particles of a gas when you heat them and cool them. So let's take a look. Paul, can you take us to this video? Here, this is a pretty easy thing to do if you have a basketball, a pump, and a scale. Basically, we deflated a basketball pretty much as I could and put it on a gram scale, and it's 576 grams. In case you can't see it, we're coming real close. Yes, 576. And then we pumped it up, put pretty much as much air as we could into it, and put it back on the scale. And it was 576 before, and now it's 581. And we didn't do anything to that basketball other than add air to it. And it's outside, it's normal air. So the air that we put in there must weigh about 5 grams. And we can go back to the presentation. And so you can say to kids, well, okay, that means the air must be matter under our definition. If matter is anything that has mass and takes up space, took up space in the basketball, that's for sure, and it had mass. So we're good. That gas is matter. So let's see what a gas is like. Again, we have kids draw and describe what they think, and we also have an animation. You can run this one, Paul. So here, if you go to the play, we finally have all 3 states of matter here. Mine starts off with a solid. Then I take a look at liquid, which I already know about, and then gas. And there should be a striking difference between a gas and either a solid or a liquid. Solid and liquid are often referred to as condensed states. They're kind of similar in a way, but a gas is pretty different. So then you would ask kids, well, look at this. This is a crazy thing. The gas particles are moving all over the place. There are not that many of them, it seems, in this, in this space, and they just hit each other and bounce off. What do you think? Do you think they're very attracted to each other or not? I'm going to stop it here and go back to the presentation. But this idea of a particle hitting another particle and bouncing off, or not coming together much to form a liquid or a solid, that's supposed to mean to a kid that, wow, maybe they're not very attracted to each other if they don't become a solid or a liquid at room temperature. So that's what we're trying to have kids understand, that the solid, the liquid, and the gas were all at the same temperature. They're all at room temperature. We didn't heat one up to make it be a gas. It was just a gas anyway. It's the gases in air. But there must be something about those particles that they don't stay together as a liquid. They definitely don't stay together as a solid. They're very far apart, not that many of them, relatively speaking, and they hit and bounce off. So their attractions must be pretty weak. So we established that, and then the same question we had before. What does a gas do when you heat it? What happens to the particles of a gas when they're heated or cooled? Well, there's a kind of an easy, simple experiment you can do. Here we can run this one, where you just take a little 8-ounce bottle, was a water bottle that's empty now, and you dip it in like a detergent solution. We use Dawn dishwashing liquid and water, and then we put the bottom of the bottle in hot water, and it forms a bubble, as you see, and then we put it in cold water. And kids love doing this. Actually, we do this at different professional development sessions, and teachers love doing this too. it's a simple way of showing a kind of a big idea. So what happened there? That's the question. Now, it's a little trickier, unfortunately, I think, than the solid and the liquid. Since the particles of a gas are not very attracted to each other, you can't use the explanation that, well, since we heated them, they move faster and overcame their attractions, and therefore they move further apart. Because their attractions are so weak, you don't really have to worry about overcoming them. So that's not quite the right explanation for this phenomena. Like I said, unfortunately, you have to kind of think a little differently about this. Here's what we try to tell kids, or have them understand. Let me grab a hand here. I'm not good at this. Okay. The bottle had particles, had gas molecules in it, oxygen, nitrogen, and they were at room temperature. So we put the bottle in hot water, and that made the particles move faster. Now, there's some arrows out here which are supposed to indicate the outside air pressure, and that's always pushing down on everything. Now, the inside particles of air, now that they've been in hot water, are moving really, really fast. They start hitting the sides of the bottle harder and more often. That's another way of saying their pressure increases. They hit the film, the bubble film that's on the mouth of the bottle, and they hit it hard enough with enough pressure, shown by these arrows, that it actually is greater than the outside air pressure, and it pushes against the outside air pressure, and the bubble forms. So they didn't really have to overcome any attractions in order to do this. They just moved faster, and they were in like an expandable environment, kind of, because it had the bubble film at the top, so they were able to spread out and push up and against the outside air pressure. And remember when we had the bubble and then we put it in cold water, they slowed down. They didn't hit the inside of the bottle as hard. That's less pressure, shown by these smaller arrows. That was the idea, to try to show that. The outside air pressure is the same as it was up here, but now the outside air pressure is stronger than the inside, and it pushes the bubble back down. You can't really say that the particles move slow enough that their attractions brought them together, like we did in the solid and the liquid. That's not really what's happening here because the attractions are so weak. In fact, you guys know that how much you would need to cool a gas to make the particles come appreciably closer together. To make these become a liquid, like liquid nitrogen, for instance, you'd have to cool it down a ridiculous amount. Liquid oxygen, same way. So you're not relying on the attractions of the gas particles for this phenomena that we're seeing here. That's a little tricky, but let's, here's an animation. Now, before you run this, Paul, can I just, it goes kind of quickly. You're going to see the bottle get placed in hot water, and you're going to see these arrows are the outside air pressure. You're going to see the bubble move up against them, and then immediately the bottle's going to go into cold water, and then you'll see the outside air pressure push the bottle in. So let's run that, and we'll see how it goes. So you guys just go down and hit that button here. It's going into hot water, and that's the outside air pressure, and the particles are moving relatively quickly. They're pushing up on the bubble film, which expands against the pressure, the outside air pressure. Now they're moving more slowly and not as much pressure on the inside of the bottle, so the outside air pressure pushes the bubble in. I personally would like a gas to behave like a solid and a liquid as far as attractions and motion goes, but you can't really explain it the same way. We can go back to the presentation. So then, this is another example where I'm giving you guys a little bit more information than what we give to kids. Whoops, not good at grabbing the hand. I'm going to try one more time. Grab the hand. Okay. Okay, I'm going to try to grab the hand here. This is my last attempt. Got it. Okay. This is nitrogen. Like almost 80% of the air is nitrogen, and about around 20% is oxygen. But look, here we've got N2, nitrogen gas. Kids get confused about these terms, nitrogen and oxygen. They think of nitrogen like on the periodic table, which is just the atom nitrogen. But we talk, that we talk about nitrogen, but really what we mean is N2, oxygen gas. But this is a covalent bond between these two nitrogens. Basically, since it's nitrogen and nitrogen, there's no difference in the ability of these atoms to attract electrons. They attract them equally well. So it's not a polar situation at all, like water is. It's just a perfectly neutral, non-polar gas molecule that has no reason, really, to bond to anybody else. Oxygen is the same way. One oxygen atom and another oxygen atom covalently bonded. There's no difference between them. There's no polarity. They're going to hit and bounce off unless you make them very, very cold. And then there's principles about why they will attract each other eventually when they're very, very cold. I don't know if you guys talk. I doubt if you discuss these things with students, but there's London dispersion forces and things, but let's not get into that at all. But since these are nonpolar, they're not going to attract each other much at all. So here is our review slide for gases that kids have drawn on their activity sheet. They've drawn pictures of a gas. If you notice, there are two motion lines on the gas particles, just like there were on two motion lines on the solid and two motion lines on the liquid. They're all at the same temperature. There's no problem there. They're all at room temperature. But the attractions that gas particles have for each other are very weak. So their motion can easily keep them apart. So they just move independently as a gas. But if you add energy, in other words, heat them, their motion will increase, and they'll move further apart if they can. I mean, if they're in a closed container that's completely closed, rigid container, they'll just move faster. They can't move further apart. There's nowhere to go. But if you have like a balloon or a bubble film, then they have the ability to, if they move faster, they can spread out more. And if you remove energy or cool them, they'll slow down, and they won't move closer together unless there's something to push them, like the elasticity of a balloon or outside air pressure, like in our example. Unless you make them extremely cold, then they'll eventually condense. All right, let's see where we are. Okay, Paul, in this one, I wanted to ask people if presenting this stuff in this way to students, if they had the feeling that this idea of the balance between the attractions the particles have for each other and the motion that the particles have at that temperature, that competition or that balance determines whether a substance is a solid, a liquid, or gas. If kids would be helped by all this stuff that we've gone through. So could you take it from here?
Sure thing, Jim. Thank you very much. And I have given you the access to the tools, and you are asked to use the clip art once again in row 7 of the tools. And if you were not here for the intro, you should see a tool column right next to the participant and chat windows, and ask you to grab column or row 7 rather, and that is the clip art. And in there you'll see a bunch of menus where you can drop pieces of clip art on there. Just click on the clip art itself and drop it onto the continuum where you think it falls with regard to helping student understanding. And it looks like most of them have caught on to that. So I'll pass it back to you, Jim.
Okay. Well, yeah, I would hope that at least there would be a moderate understanding. This stuff is not easy for a young kid, a middle schooler, to think of anything at the particulate level is a challenge. But it seems like that at least you guys think that, unless you're just being nice, that maybe going through this series of animations, drawings, activities might help a kid understand why something is a solid, liquid, or gas. We thought that this might be worth looking at. The new science frameworks actually spend a fair amount of time on modeling the particulate nature of matter. And we've noticed that we don't see many textbooks that sort of approach solids, liquids, and gases in this way. They seem to leap directly to changes of state instead of trying to maybe think about why something is the state that it's in. So anyway, that's good to see that at least you guys think it's worth a try. All right. And like I said, the new frameworks are out, and they're working on standards, as you guys know. Just very quickly, I think our lessons do follow the idea behind the frameworks. They absolutely hit a core idea, in this case, the particle nature of solids, liquids, and gases. Kids use a lot of models. They call that science and engineering practices. They carry out investigations. They construct explanations. And there are these big ideas or these cross-cutting concepts of, they talk about systems and systems models, cause and effect, adding energy, taking away energy, what that might, how that affects a solid, liquid, or gas. So I think we're in the right neighborhood for the new frameworks. Let's see if I can make my, yes. I think that's all I have. Paul, you want to take it over from here?
Yes, sir. Thank you very much. And yes, please, thank you, Jeff, for leading us there. And a round of applause there. Again, this is under the smiley face button underneath your name there. You'll find your emoticons. And give Jim a round of applause, as well as his colleagues, Patty and Adam, for their contribution on the chat and for helping guide us through that. And we would like to thank the American Chemical Society for sponsoring tonight's program. We'd like to remind you to join us in the Learning Center, where you can register for future web seminars. Join us on our community forums, in which there are community forums dedicated to the next generation science standards, which Jim just mentioned there. In the end, we'd like to thank the administration of the National Science Teachers Association for their support for web seminars. And I'd like to bring your attention to the upcoming programs, starting with next week at the NASA Explorer School Series, Chemistry of Water, Math and Science at Work, A Breath of Fresh Air. On June 4th, another NES program, Engineering Design Challenge, Forces and Motion, the Great Boomerang Challenge. And then on June 11th, with UCAR, the first in a series from them, Teaching Climate with Models, Breathing of the Earth. If you are watching this program on an archive, we hope to see you soon on a live web seminar.